Swayam Prabha. Digital India. Educated India.
The last presentation for the session is once again online, so hopefully we will not face any instabilities or uncertainties there. This is by Shashank. He's able to make it in person today. He's situated in the US right now, and he's going to present his work on a web-based test bed for studying the interactions between model predictive control and human operators. So Shashank, you're able to hear us clearly. Can you confirm?
Yes, I am able to hear.
Yeah. So shall we then get started?
Sure.
Yeah, good. Over to you. You have about 17 minutes.
It's nice to be back at IIT once again. Hello everyone. So I'm Shashank here. I'm currently a first year PhD student at UT Austin, and now my presentation will be focused on the web-based testbed I developed for the purpose of gaining insights into the interactions between model predictive control and human operators during my final year at IIT Madras. And so first of all, so I like to tell that it's observed that a major cause of underperformance, even when automation is present and working fine, could be the lack of trust of operators in control actions chosen by the automation itself. As we know, the MPC algorithm solves a multivariable constrained optimization problem periodically, and single MPC controlling MIMO systems is bound to take actions which are difficult to physically interpret. And those operators accustomed to working with CISO loops could become confused, and trust in MPC has shown to reduce among these operators in plants. And MPC performance decay over time is also a widely reported fact. And this could be caused by equipment fouling or problems in instruments, etc., or sensor or actuator faults, which result in performance deterioration ultimately. And all of these factors contribute and play a role in decreased trust in advanced process control layer of operators over a period of time. And then coming to the issue of mental workload, since tens of variables are involved in the APC layer, it becomes challenging to keep track of the information about many variables. And this is also exacerbated by information being distributed across multiple screens and displaying values without reference to their expected values is also hardly of any use, which is quite intuitive since operators then will have to remember relevant values and might need to perform mental calculations time and again, and this will also worsen their mental workload. And analog displays are therefore better suited in this regard, since an indication of their upper and lower limits is automatically integrated into the display. And all of these factors motivate a systematic study of operator interactions with the human machine interface, or HMI. And although there have been studies that address such issues, the literature lacks a standardized test bed that can be used as a problem, like a challenge problem, and a platform to demonstrate techniques or display innovations in the HMI display and GUI designs. And having said that, now let's look into the details of this testbed that I was involved with, and subsequently the graphical user interface itself. This testbed implements a hierarchical control structure, and it provides a GUI for control room operators. It aims to do so, and ultimately to enable studies of interactions of operators with similar systems. And this is a chemical process consisting of like two CSTRs in series, where there are two irreversible first order exothermic reactions of the form shown here. And reactant A is assumed to have the highest relative volatility, and hence is the predominant component in the vapor phase in the separator. And the goal is to manipulate the reactor and separator temperatures here to achieve desired compositions of the product B in the bottom stream of the separator, which is the desired product, ultimate product. And PI controllers for temperature are tuned for the same purpose using the sequential loop tuning method by Horvitz-Kogestad, and this is done a priori. And let's come to the APC layer formulation. So here, actually, like I have implemented a linear quadratic regulator, which differs from the standard dynamic matrix control algorithm of the MPC, in that the LQR optimizes over the entire time frame, and hence the same single solution is used over the entire time horizon, while the DMC computes a new solution periodically, since the optimization problem is solved in a receding horizon in the latter. And the LQR is meant to serve as an initial approximation to the DMC in this particular testbed, since this is a web-based testbed and it is computationally less expensive, and this makes a huge difference in web-based applications. For the same reason, the input constraints are also accounted for, by direct chopping instead of solving a cumbersome constraint optimization problem. And the DMC algorithm is also like, more rigorous in that it doesn't assume linearity, unlike this particular framework, the LQR. And the popularly known dynamic programming approach is used to obtain the state space matrix of the linear controller. And this is done in a finite horizon. And basically what happens here is that the LQR determines the set points of each of the lower level temperature PI controllers, which were tuned, as I said earlier. And they try to maximize the composition of the product B in the bottom stream. And hence the manipulated variables for the APC layer should be the operating temperatures of the 3 units. And since the inlet flow rates are measurable and yet cannot be manipulated directly, since they are determined by upstream conditions, these are the measured disturbances in this particular system. And the sampling interval of the regulatory controllers is chosen to be 1 second of process time, while that of the LQR is chosen to be 20 seconds of process time, meaning the lower level controllers like act 20 times faster when compared to the advanced process control layer. And one more thing, like however, in this particular process, the state space matrices of the system A and B do not form a controllable pair. And the rate-based formulation of the LQR is used rather than the direct one. And an equivalent representation of the state space matrices is done by like appropriately augmenting the existing system state space matrices, and the augmented matrices form a controllable pair. And hence this approach is used here. And now we come to the testbed itself, the web-based testbed. So this is supposed to be the login page of the website that is capable of hosting multiple experiments, and my testbed is one of the many experiments that can be hosted. And once the test subjects or the control room operators log into this particular experiment, they can click on this I am ready blue button, and once they read the pop-up message, which tells that they are supposed to be acting as a control room operator for this particular period of time. And this is a snapshot of the running simulation at a random instant of time which I took. And the users are expected to run the process for 2000 seconds of process time, and each second of wall clock or real time corresponds to around 7 seconds of process time. And since this is a simulation, like and sliders cannot be manipulated while in the A mode. I'm not sure if it's very visible, but these yellow boxes represent the lower level regulatory controllers, where like A means the PA controller mode is on, and M means it's manual control and PA controllers turned off. And sliders cannot be manipulated while in the A mode, while the PA controllers are active. And although the temperature set points can be manipulated by using the mouse, even in the A mode, of course, these white boxes basically show the temperature set points to each of the lower level controllers. It can be manipulated by the mouse and cannot be done by the keyboard. And this is for a particular reason. And alarms are indicated by red colored text as shown here. And the alarm summary table also is indicative of the same alarm display. And like when an alarm is displayed, the user would obviously naturally like to look at the trend of the particular variable, like in the past few hundred seconds or so, and this can be obtained by clicking on the blue colored icons here in this particular screen, and clicking on it once shows the real-time plot here, trend plot, and it is updated real time, while clicking on it again like turns it off, like it's a toggle switch. And apart from that, the user is also given the freedom to stop the simulation whenever they feel like doing so. And here we also see that new rows are added to the alarm summary table as alarms are generated. And once a variable reaches its normal limits, that particular row should disappear. And hence, this is not a history of the alarms generated over the entire duration, and it is only the current alarm status. And this table is meant to be scrollable for since there's only finite amount of space on the screen. And also the APC layer is active over here, like indicated by this MPC mode on, says on. And the temperature set points in this scenario cannot be manually manipulated while the LQR is turned on, since the LQR provides the set points to each of these controllers. And there is also visual indication of the same, like these boxes are slightly opaque now, rather than the more transparent ones in the previous slide here, maybe. And since users could perform experiments from any PC, it is also important to ensure that the size of the GUI screen adapts itself to the actual screen size. And in this case, the HMI screen becomes a scrollable one upon reduction of screen size, as shown here. And all front-end features, along with all calculations, including the matrix algebraic computations, are performed client-side using JavaScript. And all data related to the process and the user's mouse pointer positions are stored locally. They're stored on client-side until the user finishes performing the experiments. The user is supposed to perform 6 tasks here. And each of the tasks contain faults. I'll come back to that in a bit. And all the data are transferred to server side once the entire experiment is complete. Having said that, so this was an attempt at integrating an open source eye gaze tracker, which requires a webcam on the user's PC. And since there have been studies in certain safety critical domains like aviation, which show that operators' level of awareness is inferred by, this eye gaze tracking is a pretty good indicator of human error. This attempt was done, but it hasn't been successful so far. And the problem was that the gaze dot over here marked in red is supposed to be indicative of the position on the screen at which the user is looking. and its calibration is required prior to the beginning of the experiments. However, in this case, in our case, the gaze prediction accuracy has been poor, and this has been the same. This has been the case, like even without the user wearing eyeglasses, since glasses can be thought of as uh, uh, as an obstacle to the prediction accuracy. But even without eyeglasses, there seems to be some problem, and this like hasn't been solved yet. So this eye gaze tracker had been dropped for the time being. And now like I'd like to explain the experimental procedure.
Shashank,
That was
Shashank, sorry for interrupting you. You have about 2 to 3 minutes at max.
sure. Okay. So here, like 7 candidates, and none of whom had prior experience in this domain, were given a set of instructions with respect to website usage. And they were given a brief description of the process. And this lasted around 15 minutes, and 6 tasks in total, where different sensor developed faults in each task, and the nature of task faults remained the same. Like in each task, one or the other sensor would become stuck. Not more than one sensor became stuck. So since the likelihood is low for the same. And the overall process would have lasted around 20 and 40 minutes, depending on the user's ability to sustain the process without shutting down. And here are some observations, preliminary observations. And on an average, the simulated system went to an emergency shutdown stage with a mean runtime of 33% of the stipulated process runtime. And this is a high number, and this indicates the need for operator training. And also observed a mean runtime of just 23% in scenarios where users clicked on stop and directly exited the task. And this indicated participant fatigue. And also, we see that the LQR has been only sparsely used, and this could be due to the fact that liquid level has been the most important variable triggering automatic shutdown, and could also be a reflection of the lack of operator experience, since they seem to be more inclined to prevent the process from shutting down instead of trying to maximize product compositions. And a few other observations are listed here. Liquid levels and flow rates are the main variables that resulted in automatic process shutdowns. And most users were unable to bring all variables back to their original, like within normal operational limits. And at least one row in the alarm summary table was always filled. And there have to be further refinements to the LQR and the website, since the simulation was also like found to slow down a bit after half or 1,000 seconds of process time. And like mentioned earlier, like I guess data would also provide greater insights, and this also has to be incorporated in the future. And also, like adding predictions to the control signals predicted by the MPC to the same trend plots could be a way to improve the trust in MPC, and this also should be incorporated. And here are the references, and thank you.
We have time for a couple of questions. Yeah.
So I have a couple of questions. So first one is related to your GUI, what you have shown. So I just wanted to know how you have placed your different variables on the GUI. So did you use some heuristic to place different variables? How the person will know that the variables that are associated closer to each other are they related causally, or some other reasons? Then
Actually, like so here there are, in this slide, if it's visible, I hope it's visible. Like, so these blue icons are indicative of basically, for example, this particular icon is indicative of the level in tank 3 or the separator, and right adjacent to it is the value of the level, exact level. and here it's the flow rate from the separator that goes out as purge, etc. So the user should not have much difficulty in identifying which variable corresponds to what, since the the labeling, the markings with like, for example, LC means level controller, TT means temperature transmitter. So close to TT, there's a temperature reading which represents the temperature in this tank 3, etc.
Yeah, I think about it. So just follow-up question. That you mentioned in the conclusion slide that variables which triggered shutdown were 301 and I think 303. So do we have a reason that why these variables triggered shutdown? Is there a lack of knowledge from the operators, or is the design issue with the design of the whichever?
I think it is a combination of both, more or combination of both, although I'd say like lack of operator experience is the more prominent factor. Since over here, what I think is like this screen accommodates only like certain sizes of the certain lengths of these scroll bars, and the users are supposed to click and drag on them, click on them and drag these to manually manipulate them. So I think what happens is that in manual control, they might dragging it even a bit too much, like, dragging it even a few pixels or so could result in a large change in the flow rate. This is as far as manual control is concerned, since the sliders are pretty small, I'd say. So I guess that is one of the things that I observe here.
Okay.
Thank you.
Yeah.
So thank you, Shashank, for answering those questions. Slightly beyond time, unless there's an extremely quick question, very quick question, I would like to close this presentation and session.
Yeah, one session, sir. Thanks for the presentation. This was quite interesting and focused problem 5 years ago. I think it evolved a lot. Now, most of the vendors solve this problem with different HMI, which tells what is the control move, what is the optimization move. There's a lot of analytic information provided to user on the HMI itself. So maybe we can revisit some of our assumptions while selecting the problem. Right?
Sure. Yeah, thank you. Thank you for those remarks. So Shashank, I take this opportunity to thank you once again on behalf of everyone here for a nice presentation. And I suppose it is sleep time for you, or?
Yeah, so I have an exam in a few hours. So,
Okay. So I think you have trained you well enough.
Yeah.
Right.
Thank you so much for the opportunities. Yeah.
Thanks, Shashank, for joining us. And yeah, let's thank the speaker once again. Yeah. So with this, we close this session, today's session at particular one, the 2 to 3:21. And I think we have a short break, I suppose, now.
Tea break.
Yeah, so please join us for tea. And I think all the 4 presentations here were very interesting. I'm glad to see that there is a session which still, dedicated to pure control without invoking AI and ML and so on, which is very good. And I hope that this will be the case for future. All right, so I take leave. It was a pleasure chairing this session. And on behalf of everyone, I would like to thank once again the speakers and the authors of the works that were presented today. Thank you.